Hello everyone, I am Aman back with another beautiful question on binary trees. So the question for today is we are given a binary tree, we have to find its node to root path. Okay, so I'll explain the question later on because before that we need to do one other question. Okay, so let's just do this question very quick. You already know this if you are watching this video. If you have reached at this level of tree, 100% you know this question. So the question is, let's first do that question. Given a binary tree which contains all unique values, search if there exists a D in a binary tree. Or D, or let's just say K sounds better. So let's just search for a value K. I want to know simply if there are K equal to 6 or a particular K value exists or not in a binary tree. So this is a binary tree given to me. So let's just quickly start searching. So you can do any kind of traversal in order pre-order, post-order, right? You basically understand how you're going to do that. You'll just traverse over the tree and check if 6 exists or not. So let me just give a quick dry run to you how it will happen. So we are at the root. Root will ask, root will check if I am equal to 6, the currently the value that we are looking for. No, then it will ask its left subtree and then right subtree. Okay, then 7 is not equal to 6, so 7 will also ask its left subtree and right subtree. Now we reach 9 is not equal to 6, so it will ask its left subtree and right subtree. So we reach to 12, we reach to 19. 12 will ask its left subtree, right subtree, both of them will return false. 12 is also not equal to that, so 12 will overall return false. Now 9 asked its left subtree, it got a false. From right subtree also it will get a false, so it will also return a false. Now 9 is not equal to 6. Left subtree is saying I don't contain 6. Right subtree is also saying the same. So 9 will also return false. Now coming to 7. 7 is not equal to 6. And in its children, it doesn't have a 6. So it will also return false. Now we reach to 3. 3 got false from its left side. But 3 will check from its right side also. So we reach to 4 then. 4 will say, okay, I'm not equal to data. But let me check with my left and right subtree. Now we use this 14 said, okay, I'm not equal to data, let me check with my left and right subtree. So you understand, first left call happens. So let me show you it properly. First from 14, first we'll go to left subtree and then we go to the right subtree. So we reached 15. 15 said, okay, I'm not equal to data, let me check with my children. Both the children are null, so it will return false. Children will return false to them. 15 will overall return false. 15 return false. Now coming to this 14. 14 got a false from its left subtree. Now 14 will ask its right subtree. We reach the right subtree. 12 said, okay, I'm not equal to data, let me ask my children. So once we reach here at 6, 6 will say, yes, I am equal to the data that you're looking for. So what do? 6 will return what? 6 will return true. Now minus 12 asked its left child and right child. From left child it got a false, from right child it got a true. So it means it in right subtree the data exists, so it will return overall true. Now similarly 14 asked left and right child, from right side it got a true, so it will return the true. Now coming to 4, 4 got a true from left side, so it won't make the call to the right side, right? This is the way in order happens. We first, or pre-order happens. We are doing pre-order here actually, because we are checking with ourselves, then we call for the left and right. So we 4 was not equal to data, left side it got true, so it will return true. It don't need to check on the other side. Now 3 will say, okay, right child is saying that it contains the data. It means yeah, the data exists, and this is how the calls will happen. If I have to write the code bool check, I am given node root and let's just say int d, and then what? Simple. First thing is, if you reach any node, you will check if you are equal to data. So if return root.data double equals to d, you return true. Otherwise you make call to your left or right side. So you recursively call check function for your left subtree, root.left comma d, or check root.right comma d. If any of them return true, it means I can return true. Hope it makes sense to all of you. And if nothing this sort of happens, overall will return false. So this is how the code will be. And base case is simple. When 12 asks its left and right child and they are null, so they should return false. So if root double equals to null, they return false. So now we know how to check whether a particular value exists in the tree or not, correct? In a binary tree. In BST, checking is even faster. You can skip one child left or right. You can skip one half of the part, right? Every time. Now let's come to the actual question. So the actual question is called node to root path. Let me copy the tree and a k value. So you are given this tree and you are given a value k equal to 6. You have to give node to root path. This is node 6. You have to give this path. Maybe you have to return this in a list. So this is what you're supposed to return: 6 minus 12, 14, 4 and 3. If k value is given as 9, then you will return 973. It's not compulsory that you will find the data at leaf, right? Or it can happen you never find the data. So how are you going to do that? The way I'll simply explain for 6 and you can get it. So friends, if you notice carefully, you just have to notice it very carefully. Okay, let me remove some extra things, then you can I think you will be able to view it more properly. I want to return this particular set. I want to return these set of nodes. What unique property do you feel they have right now? I mean, is there something different from other nodes that they possess right now? Yes, if you look carefully, they all are those nodes which are returning true. Yes or no? These all are all the nodes which are returning true when I was looking for k equal to 6. So what do we have to do now? Simple. I just have to store the element whenever a node is returning true. That's all. I mean, this minus 12 was returning true, so I'll add it to my list. This 19 was returning false, so I won't add it to my list. So let me just copy paste the code and I'll do a quick dry run for you. So let's just write the code. The same code I will use. Let's just say I create a list of node, because I want to store all the nodes. List of node is equal to path. And then what? Simple. If root dot data double equals to d, it means this particular node is returning true, so I should store it. So path dot add this particular root node, and then here also when I was returning true, I should add this node, path dot add root. What if I tell you this is it? You have done it actually. Maybe you're not very clear with the code, but this is it actually. So let's just see how it will happen one more time. So let me clear out everything and I'll do it in a very quick manner because I'm very sure you will understand it very easily now. So this is my list initially completely empty. Now I am at 3. 3 is not equal to data, so it will ask its left child and its right child. Left child first, first we will come back from the left subtree, then I will go to the right. So we are at 7. 7 is not equal to data, so it will ask its left subtree. 9 will ask its left and right subtree. All of these guys are returning false, 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 and this 7 also returned false, so none of them I added in the tree. Now let's see the other side. We reached to 4. 4 said I am not equal to data, but let me check with my children. So first left call will happen, and this whole subtree, once we come back out of this tree, then we make call to the right child, right? This is how recursion works. So we reached to the 15. 15 checked with its children. 15 also returned false. Now we are at 14. 14 called its children minus 12, and minus 12 called 6. 6 said okay, I am equal to data, so I am returning true. This is what point in your code if root dot data is double equals to d. So what you are doing, you are adding it to your path. So you added 6 and then you did what? You returned true. So this 6 returned true. Now I am at minus 12. What did you do at minus 12? When you were at minus 12, you said I am not equal to data. Check, let me check with my left and right child, and then if any of them returns true, it means I can say yes, I have the data. I mean, there is data is within me somewhere. This call is represented how? Here, this when your root value is minus 12, that's how you can get it. You check with your left child, you check with your right child. In this case, what would have happened? Right call must have returned true. So that is why we want to add this guy also. Now when we are at minus 12, simple. What would have happened? When we are at minus 12, we are basically representing this particular part, that root value is minus 12. Root says okay, I am not equal to data. I called for my left and right side. My right side returned true. That is why the 12 was supposed to return true. Since 12 is supposed to return true, before that 12 will also get added in the list. So 12 is also added. Now let's see it one more time. When you reach to this 14, when you were this 14, you were not equal to data, but you called for your left and right side. Left side return false, but right side return true. So what do? You were also going to return true, this 14, and before that we will store you up. This is how it will happen, so on and so forth. Hope it makes sense. Now coming to time complexity, in the worst case we can traverse the whole tree. So time complexity is order of n. Coming to space, now one time what can happen at max, first these many functions will be there in the stack. Now once this 12 gets removed, these all functions will be there on the stack, right? So at max, order of h function, whatever is the height of the tree, that many functions can be there in the stack. Hope it makes sense to all of you. Thank you so much. See you in the next video.